Hello, everyone. Today I'm going to talk about some great developments in the theoretical guarantees for deep generative models, specifically through the idea of PSA bias theory. My representation will focus on two important papers: Peck-Bayesian generalization bounds for adversarial generative models that is published by SML, and statistics guarantee for variational autoencoders using Peck-Bayesian theory that is published by Lurips. We will be exploring two types of generative models: the adversary generative models and the variational autoencoders, and how Peck-Bayesian theory helps us to understand their ability to generalize to new data. Understanding the generalization ability of these models is significant because in such way, we can develop some tricks to improve their reliability and performance across a wide range of applications. Generative models have become a hot point in machine learning. They have been widely used for tasks such as image generation, text generation, and even in areas such as medical data augmentation. However, despite their wide use, we still face significant challenge. How do we know whether a generative model generalizes well to new and unseen data? This is an especially difficult problem because it's hard to define clear metrics for generalization in the context of unsupervised learning models, like those we will discuss today, the GAN and the VAE. PSA Bayesian theory provides a framework to address this challenge. It offers
Found this on the web to provide a framework to
probabilistic bounds that allow us to assess how well a model is likely to perform on new data. The theory is particularly well suited for studying complex models like generative models because it doesn't require many assumptions about the data or the model itself. In this presentation, I will show you how Peck-Bayesian theory is applied to two types of models, the GANs and the VLEs, to derive theoretical guarantees on their performance. And first, let's talk about the generative modeling. Generative modeling is a key area in machine learning where we aim to create models that are capable of generating new samples that resemble the training data. Given a set of finite, independently and identically distributed samples, the model's goal is to learn the underlying distribution of the data and generating new samples from that distribution. For example, there are two pictures in the slides. You can see that it comes from the Minnesota test. The MINIS dataset consists of many handwritten digits, and we want to use some data from this dataset to train our model, to train our generative model. And the goal is to learn to generative sample from the same distribution. Here we want to produce some handwritten digits that are very similar to the given samples. Just like the generative dataset, the generated data is still written by hand. This is particularly important in applications like image generation, where we train the model on thousands of real images and then expect it to generate new synthetic images that are indistinguishable from the real ones. Generative modeling are trained is used in a variety of other domains too, including natural language processing, where models are trained to generate coherent, coherent text, and bioinformatics, where they can be used to simulate protein structures. The quality of these models depends heavily on their ability to generalize beyond the specific examples in the training data. The intuition behind generative models is that they transform random noise into structured data. These data are similar to real-world samples. Imagine feeding random numbers into a neural network and having it output an image of a human face or landscape. What the model is learning is how to map this random noise to something meaningful based on the patterns that the model has learned from the training data. For instance, in the case of image generation, the model learns features like textures, colors, and shapes that are common across the training images, and it uses this learned information to generate new images that look like they belong to the same distribution as the original ones. The model does this by capturing the underlying statistic patterns in the training data, and then applying those patterns to create new instances. Here we want to learn from the training data and generate some digits that are just like it is written by the human beings. Analyzing generative models is much more complex than analyzing traditional supervised learning models. One of the biggest challenges is that the true data generating distribution is unknown. We don't have access to the exact mathematical formulation that describes how real-world data is produced. As a result, we can't directly measure the accuracy of our models in the way we would with supervised models, where we can compare prediction labels with actual labels. Furthermore, there are many different ways to measure the similarity between the true data distribution and the generated data distribution. Each method of measuring similarity, whether it's based on distance metrics, such as Wasserstein distance, or divergence measures, like KL divergence and JR divergence, gives a slightly different perspective on how well the model is performing. This makes it harder to define a universal criterion for what it means for a generative model to be good. Yes, how can we what it means for a generative model to be good? Just as the principle to determine this is that we need to show that our generative model can learn the distribution that just as close as to the true data distribution, then the generative model is good. Tech Bayesian theory offers a robust and flexible framework for tackling the challenges of generalization in machine learning models. Tech Bayes provides high probability generalization bounds, which means it can give us probabilistic, probabilistic guarantees that a model's performance on new unseen data will be close to its performance on the training data. One of the key strengths of tech bias is that it makes very few assumptions about the data or the model itself. In particular, it doesn't require us to know the true data generating distribution. This makes it especially useful for generative models, where the distribution of the data is often highly complex and unknown. We can only learn the distribution according to the training data, and in fact we don't know how the training data is produced and what distribution it according to. Additionally, Peck-Bayesian bounds are numerically computable, which means we can actually calculate these bounds in practice and use them to guide the development of our models. Let's break down some of the core concepts that Peck-Bayesian theory uses. First, we have the instance space, which is a set of all possible inputs in a generative model. This could be something like the space of all possible images. We also have an unknown distribution over this instance space, which represents the true data generating process that we are trying to approximate. Next, we have a set of observations, which are the samples we have access to. These are drawn from unknown distribution, and our task is to learn from them. Finally, we have the hypothesis space, which is a set of models we are considering. In Peck-Bayes, we don't just look at individual models. We often consider aggregate hypotheses, which are distribution over the set of possible models. So we don't consider the individual hypothesis. We consider aggregate hypothesis, and we will define the prior distribution over the aggregate hypothesis and the posterior distribution over the aggregate hypothesis. In Peck-Bayes, we deal with two types of risk: empirical risk and true risk. The empirical risk measures how well the model performs on the training data. It's essentially the model's error on the data we have seen. On the other hand, the true risk measures the model's error on the entire distribution of possible data, including data that we haven't seen yet. The challenge is that we cannot directly measure the true risk because we don't know the true data distribution. What Peck-Bayesian theory gives us is a way to bound the true risk based on the empirical risk. In other words, it allows us to say with high probability that the model's performance on new data will not be much worse than its performance on the training data. So this is what's the meaning of this bound. KL divergence. KL divergence plays a critical role in Peck-Bayesian theory. It measures how different two probability distributions are. In the context of Peck-Bayes, we use KL divergence to compare the posterior distribution, which reflects what we have learned from the data. with the prior distribution, which represents our initial beliefs about the model before seeing any training data. The idea is to minimize the KL divergence between these two distributions, ensuring that the model we end up with after training isn't too far from our prior beliefs. This helps us to strike a balance between the fitting the data and staying true to our initial assumptions. This is important for avoiding overfitting. Here is an example of a Peck-Bayesian bound from a theorem. This bound tells us how the true risk of a model is related to its empiric risk, the KL divergence between the posterior and prior distributions, and other factors like the size of the training data of the training set. The parameter lambda controls the strength of the bound, allowing us to adjust the trade-off between trusting the data and trusting the prior. What is crucial here is that this bound gives us a high probability guarantee that the model's true risk will be close to its empirical risk. This is the essence of what a Peck-Bayesian theory offers, a rigorous way to understand how well our model will generalize to new data, even if we only have access to the training data. Now, let's turn our attention to the generative adversarial networks. This is also called GANs. GANs were introduced by Goodfellow in 2014, and they represent one of the most exciting developments in generative modeling. A GAN consists of two neural networks, a generator and a discriminator. The generator role is to create fake data that looks like the just looks like the real data, while the discriminator's role is to distinguish between the real data and the generated fake data. This setup creates an adversarial process where the generator gets better at producing realistic data, and the discriminator gets better at detecting fake data. Over time, the generator improves to a point where the discriminator can no longer reliably tell the difference between real and fake data. In a GAN, we start with an instance space, which represents all the possible data points and a data generating distribution that we're trying to model. The training set is a set of independently and identically samples from distribution, which we use to train the GAN. The generator in a GAN is a neural network that takes random noise as input and outputs a data sample. The discriminator, on the other hand, is a neural network that takes a data sample as input and outputs a prediction of whether the sample is real or generated by the generator. The two networks are trained together, with the generator trying to fool the discriminator and the discriminator trying to correctly classify the samples. The Washington distance, one of the key metrics used in analyzing GANs, is the Washington distance, which measures the distance between two probability distributions. The Washington distance is often preferred over other metrics, such as the Jensen-Shannon divergence, because it provides a more stable and meaningful measure of how far apart the two data distribution and the generated data distribution are. In fact, the Wassenstein gun is an important improvement for the original gun. Intuitively, the Wassenstein distance tells us how much work is required to transfer the one distribution into another. This makes it a useful tool for guiding the training of guns, as it encourages the generator to produce data that is as close as possible to the real data. The Wassenstein gun. In the Wassenstein gun framework, the goal is to minimize the Wassenstein distance between the true data distribution and the generated data distribution. The discriminator or critical in this framework estimates the Wassenstein distance, and the generator is trained to minimize this distance. One of the advantages of using the Wassenstein distance is that it leads to more stable training compared to traditional guns, which can suffer from issues like model collapse. Model collapse happens when the generator produces a limited variety of outputs, but the Wassenstein distance helps avoid this by providing a smoother optimization landscape. In the context of GANs, we define the risk in terms of the distance between the true data distribution and the generated distribution. The empirical risk is based on the training data, while the true risk is based on the entire data generating distribution. Our goal is to minimize empirical risk during training, while using Peck Bayesian bounds to ensure that the true risk is also small. Here we can see that we have two samples. We have an independent and identical samples, the S. It is sampled from the distribution, the true distribution P star, and there is also a sample set SG, which is sampled from the generated distribution PG. Then because these are two distributions and we can only sample some data from them, and so we use P star n and PGN below the corresponding empirical distribution. And here are the definition of these two empirical distribution. And here we define the empirical risk of hypothesis G as this, the Wassenstein distance of the two distribution. And we use the Wassenstein distance to metric the similarity of these two distributions. To give the theorem for bounded instance space, we should first give some notations. The n-size training set S is independent and identically sampled from a distribution P star over the instance space X. Each generator induces a distribution PG. The prior distribution pi belong to the probability measure over the hypothesis space G is independent of the training data S. And there is a constant lambda, it's more than 0, and the delta is belong to 0 and 1. The critical family here is 1 Laplace is symmetric. So we can give the theorem for Wassenstein guns. This theorem gives a bound on the empirical risk for Wassenstein guns with high probability. the expected risk on unseen data will be close to the empirical risk, with an additional penalty term that accounts for the model's complexity and the number of training samples. This result gives us theoretical guarantees for how well a Wasserstein gun will perform on new data, which is crucial for applications where generalization is important. Here are some experiments with the Wasserstein guns. To validate these theoretical results, the authors performed experiments using Wasserstein guns on synthetic datasets, just as the Gaussian mixture. These experiments were designed to measure the order of magnitude of the Peck-Bayesian bond in practice. The goal was to see whether the theoretical predictions about the model's performance held true in real-world settings. Here we see the numeric results for the ring dataset. One of the synthetic datasets used in the experiments, the empirical results closely match the theoretical predictions, showing that Peck-Bayesian bonds are not only useful in theory, but also hold up in practice. This provides strong evidence that these bonds can be applied to real-world generative modeling tasks. Similarly, for the greater dataset, the theoretical bonds derived from the Peck-Bayesian theory align well with the empirical results. This consistency across different datasets reinforces the idea that Peck-Bayesian bonds provide meaningful and reliable predictions about the generalization performance of generative models. These results suggest that the framework can be used to analyze a wide range of generative models, not just GANs. Then we can apply the Peck-Bayesian theorem to the VAEs. Now let's talk about the variational autoencoders, which were introduced also in 2014. VAEs take a very different approach compared to GANs. Instead of using an adversarial process, VAEs rely on probabilistic methods, specifically variational inference, to learn a latent representation of the data. The main idea behind a VAE is that it learns a lower dimensional representation or latent space, where the data can be compressed and then uses the latent space to generate new data that resembles the original data. This probabilistic approach gives VAE some distinct advantages, especially in terms of stability during training. In a VAE, we have two spaces, the instance space, which represent the data, and the latent space, which is a lower dimensional space where the data is mapped. The model assumes that the latent variables are drawn from a standard Gaussian distribution. And the goal is to learn an encoder that maps data from the instance space to the latent space, and a decoder that maps latent variable back to the instance space. The encoder learns the parameters of a Gaussian distribution in the latent space for each data point, while the decoder learns to reconstruct the original data from these latent variables. By minimizing the reconstruction error and regularizing the latent space, the VAE learns to generate new data points that resemble the training data. The encoder in a VAE is parameterized by a neural network that outputs the parameters of a Gaussian distribution over the latent space. Specifically, for each data point, the encoder outputs a mean and a dialog covariance matrix, which define the distribution of the latent representation. The encoder thus learns a probabilistic mapping from the data space to the latent space, where each data point is associated with a probability distribution rather than a fixed point. The decoder in a VAE is a larger neural network that maps points from the latent space back to the data space. In many cases, we assume that the decoder is a Lipschitz continuous function, meaning that small changes in the latent space lead to small changes in the generated data. This smoothly constraint ensures that the decoder produces meaningful reconstructions of the data, making the model more robust and stable during training. The optimization objective in a VAE consists of two terms. The first term is a reconstruction loss, which measures how well the model can reconstruct the original data from the latent representation. This is typically done using a loss function like mean squared error or forced entropy. The second term is the KL divergence between the learned latent distribution and the prior distribution, which regularizes the latent space and ensures that it does not divide too much from the prior. The model is trained to minimize the weighted sum of these two terms, with a hyperparameter controlling the trade-off between them. This ensures that the model learns a latent representation that captures the structure of the data while remaining close to the prior distribution. Once the VAE has been trained, it can be used as a generative model. To generate new data, we sample from prior distribution in the latent space, and then pass these samples through the decoder to produce data points. The hope is that generated data will resemble the real data in terms of the statistical properties. Our goal is to ensure that the generated distribution is as close as possible to the true distribution. We can measure this closely using metrics such as sum distance or divergence, just as that we have done with GANs. Similar to GANs, we can apply Peck-Bayesian theory to VAEs to obtain the corresponding generation guarantees. When the data comes from a bounded instance space, we can derive Peck-Bayesian bounds on the Wasserstein distance between the true data distribution and the distribution generated by the VAE. These bounds provide a high probability guarantee that the VAE will generalize well to new and unseen data, giving us confidence in its ability to generate realistic data. This theorem provides a Peck-Bayesian bound on the Wasserstein distance between the true data distribution and the distribution generated by the VAE. The bound depends on several factors, including the reconstruction loss, the KL divergence, and the Lipschitz constant of the decoder. By minimizing these terms during training, we can ensure that the VAE generates high-quality data that closely resemble the true data distribution. In conclusion, generative models, whether they are GANs or VAEs, are incredibly powerful tools in machine learning, but they are also difficult to analyze. Peck-Bayes provides a rigorous theoretical framework that allows us to derive generalization guarantees for these models. The work presented today show us how Peck-Bayesian theory can be applied to both adversarial and variational generative models, offering new insights into their performance and reliability. So, by providing computable bounds, Bayesian theory gives us a way to predict how well these models will generalize to new data, which is very important for real-world applications where robustness and reliability are essential. Okay, that's all for today. Thank you.